This chapter is on near equatorial precipitation. Basically, we are going to look at the Intertropical Convergence Zone, ITCZ, and the southern parts of it, which are called the Great Cloud Bands. But we know that this is called the South Pacific Convergence Zone, and there is a South Atlantic Convergence Zone here. The idea is to try to understand the processes that determine the location of precipitation here in terms of some of the basic processes that we have been looking at. It's a very long chapter, so I'm going to go ahead and show the concluding thoughts first so that you're prepared to expect what is going to be following very rather long detailed discussions. So conclusions of the chapter we'll come back to after we finish the chapter is that the dynamics of desert that we looked at is going to have some bearing on what we are addressing here in terms of physical mechanisms that will create the pluvial regions. The ITCZ, Intertropical Convergence Zone, may lie off the equator in regions of cross-equatorial pressure gradients. That should be two words. So the pressure gradients are going to be set up by sea surface temperatures, which we don't really explain. So they force the advection of a wrong signed absolute vorticity across the equator. Obviously, we already saw that the vorticity convention we used is positive in the northern hemisphere, negative in the southern hemisphere, and if you push vorticity across, you're going to bring the opposite sign vorticity into this across the equator. Pressure gradient is the result of slowly varying SST differences, which we don't explain here, so it's taken as a given. Such an intrusion is inertially unstable. It's also called symmetric instability because of the flow being symmetric on isobaric surfaces that we will look at in a bit more detail. The cross-equatorial pressure gradient is not sufficient as static stability on the warm side of the equator must not be too great. So even if you say pushing the vorticity across the equator is going to give you an instability to drive inertial instability. If there is static stability on the other side that inhibits convection, then obviously it's not a sufficient condition, it's only a necessary condition that you push the wrong signed absolute vorticity across the equator. Such a stipulation renders the cross-equatorial monsoon flow inertially stable. So we'll see that despite being having a very strong cross-equatorial gradient in the Western Indian Ocean, the strongest, you will have no convection there, even though the region possesses strongest CEPG on the planet. The great cloud bands are predominant precipitation features of the southern hemisphere. There is some indication that the northern hemisphere also contains a cloud band with similar features to those in the southern hemisphere. So to go back quickly here, we will see a cloud band here, the so-called Mayu-Bayu front, and we already saw that the Indian Ocean behaves strangely, and this is the region I talked about in terms of cross-equatorial pressure gradient. That's not enough to give you rainfall. The equatorial part of the bands appear anchored in a warm pool region or a location of monsoon rainfall extending towards higher latitudes. So South America versus the maritime continent, you get two processes. Simple first-order dynamical arguments were used to explain the orientation as thermodynamical balance changes from a diabatic limit in the low latitudes, so the heating, to an advective limit as the zonal winds increase in higher latitudes. So there is an angular extension that has to be explained. High frequency variance changes from 20 to 40 days in the equatorial regions of the bands to high frequency multi-day variance at higher latitudes. So you will get more of a synoptic time scale at higher latitudes. Extratropical variants appear to be strongly modified by the longitudinal variability of the basic flow that we have looked at in the context of modulation of the waves, trapping of the waves, and energy trapping, and so on. So this shows a contraction of longitudinal scale and a slowing down of phase and group speeds. So ITCZ turns out to be a combination of multiple of these things. In chapter 11, we developed an argument to suggest that within the westerly duct or tropical upper tropospheric trough, potential vorticity was funneled towards the equator through reoccurring breaking Rossby waves that were generated in the unstable extratropical jet stream exit region and propagated eastward in the outflow region of the jet. The jet itself is the result of poleward advection of potential vorticity by the tropical and subtropical heat sources. So we generated upper level PV substance that was advected northward in the meridional and eddy fluxes that gave us the strong westerly jet. The jet, the reoccurring high frequency waves complete the potential vorticity balance by advecting potential vorticity back towards the equator that we saw, which then gets advected eastward by the easterlies, westward by the easterlies, and back north. So there was the loop that we saw. In essence, the ducts and the toots completed the PV balance circuit. Now, the other big question that comes up is whether convection and ITCZ happen on the warmest sea surface temperatures. If you go back to this statement by Philander in 1990, moist air rises where sea surface temperatures are highest and subsides where the surface waters are cold. This is turns out to be not that simple, that actually precipitation is not right on top of the sea surface temperature, and there is also the idea that it's the gradient and not the warmest temperatures that matter. Okay, so all these ideas have to come together in this long chapter, but you will see that most of it is kind of a consistency check, a diagnostic, an explanation of what is happening, rather than a prognostic of starting with, let's say, why the sea surface temperature distribution the way it is. There are some explanations, for example, that the ITCZ is predominantly in the northern hemisphere because of the land distribution. The land is more in the northern hemisphere. It has low heat content, so as sun moves north, it heats up and pulls the ITCZ north. But actually in the zonal mean, this difference of land effect doesn't seem to be so big. So the argument by people like John Marshall is that the overturning circulation in the ocean moves energy north across the equator in the Atlantic against the temperature gradient, because its ocean is mechanically forced to move heat, and the atmosphere is required to move the energy back south. It's called the energy equator, and that's why the ITCZ is in the north. That idea is not discussed in this book, so we will just mention it and leave it there, and then get into the processes that are important as we go along to explain bits and pieces of the ITCZ, because even though it looks like a pantropical band, actually there are different processes happening in different parts of the ITCZ, especially the Indian Ocean turns out to be quite different.